Okay, so hi all. Welcome to this first video in our last unit, I guess, as we will call it. And before we start with this, just a class reminder, I guess. In case you didn't already look, your exams from last week are posted on Canvas. I think if you just go to exam number 2, I don't know, you click on something where it sort of shows you the comments. So I attached your marked up, your graded papers there. So anyway, so you should be able to find that and look through to see how you did. Overall, we did very, very well, which is good. If you had done the the math haiku extra credit points, 1 point, or if you were the class winner for best poem about math, 2 points were added to your score. So that's already been added in. So whatever you see in Canvas is your score. So have a look through that, of course. And we'll do one more exam. So the stuff that we'll start today and do for these last few weeks, we'll have an exam number 3 at the very end of the semester, our last class period, whatever that Thursday, the 14th maybe, I think, or something like that, whatever that last week is. As you probably know or have heard, final exams have been canceled, or I shouldn't say that. Final exam week has been canceled, or repurposed is probably a better word, into just a regular week. So that last week, when we would have done final exams, is just a regular week of either classes, if your classes are doing regular stuff, or in many classes you're going to still maybe have an exam or a final exam. It's just that it'll be during your class time as opposed to these 2-hour blocks that we normally did for final exams. So in our class we're going to do an exam number 3. So it's not going to be cumulative in any way, shape, or form. It'll just be on this stuff that we do in these last few weeks. So obviously, as usual, stay tuned for more details on that. That was about it in terms of stuff. I think we'll probably get 2 homework assignments in before then, depending on how quickly we move through this and how far we get. Anyway, well, let's get started. So, oops. So if the title of this unit sounds familiar, partial differential equations. If it sounds familiar, it's because it's what's been on your schedule as this course for the whole semester. Now, of course, probably most classes that you take, the title of the course probably is addressed I don't know, day 1, maybe day 2 at the latest, instead of day, who knows what day we're up to at this point. But I think I did say at the beginning of the semester that we've renamed this class, so you are all officially the last people to ever take the class called Partial Differential Equations, at Endicott anyway, and we've just renamed it and repurposed it as Differential Equations Part 2, which I think you'd all agree is what this class has been so far. It's been a continuation of the ODEs class that you all took. And so we spent, our time together so far has been spent still in ODE world, but doing basically all the things that we didn't do in ODE's class that were interesting and important. But we leave this time at the end. Usually it's more like the second half, but since we lost a week in here, it'll be these last however many weeks here to talk about partial differential equations. So, what is this, right? Or what are we even talking about with this? So this video will be getting us off the ground and getting us with the lingo of what this is, and introducing our first model of 2 that we'll look at, known as the heat equation. So let's get our ducks in a row here and our notation in place. So let's define we'll use U. I know we've used U an awful lot this semester. Usually U is our helper function or our integrating factors. So you don't have a cute story for you as to how how we came up, or how they've come up with the fact that u is now sort of going to more normally be the name of our function, but it is. So we're going to get happy and familiar with u as the name of our function, as the name of our differential equation that we're going to try to solve. As let's define u of x. Now, if I just stopped here and said the usual definition of a differential equation, I would say let's define u of x to be a function of x, and differentially an ODE is an equation that involves the derivative of u, maybe first derivative, maybe second derivatives, and its variable x. But for partial differential equations, we're expanding our capabilities here, and we're going to expand to functions of two variables. So let's define u of x and t is how we might say that, right? So u of x and t is to be a function of two variables obviously x and t being those two variables, which are, if we were going to make a list of what do we usually name our variable, and when we only have one, we usually probably either name it x or t. And if you ever have a function with two variables, oftentimes maybe either x and y or x and t are natural choices. But since we're going to be dealing with models here, in other words, word problems, we will stick with this notation because x and t, I don't probably have to tell you, t is going to represent, of course, time, as it always does in these problems. So there's certainly going to be an element of time, so rates and things like that are going to take on our usual format here. But what's the other variable? So this is what's different about PDEs, right, partial differential equations, as compared to ODEs, ordinary differential equations, is that for ODEs, if it was a word problem, let's say, time was the variable, and there was only one variable, and it was t. Sometimes we used x, probably in ODE's class, but that was just sort of just for variety, really. But there was still only ever one variable. But of course, with partial differential equations, we're going to have two variables. So naturally, in real-life problems, t is maybe makes sense to, time, that's an independent variable, or that's something that marches on, so that makes sense that would be a variable. But what's the other sort of independent variable that we will look at? Well, x is what we're going to call it. But what does this usually represent? Is, if you want to use the fancier terms, space. Now, that doesn't mean outer space or anything like that, so maybe let me put in parentheses a better human word, which is location. So we're going to be looking at functions. So first of all, u is a function. It's a function of two variables. And what do I mean when I say u is a function of x and t? I mean u is a function, which whatever it is that it's modeling, I don't know what it is yet, but apparently location and time both influence what u is equal to. Now, if you think about your life for a minute, there are many things that depend on maybe just t, and maybe many things that depend on just where you are. But there are also probably things in your life that you could say, well, it matters when this happens and also where it happens. I'll go ahead and let you fill in a real-life example of something like that. That's what this is going to talk about, and these are going to be the kinds of problems that we're going to model here, is when we have a quantity that we're studying, and we can say, well, you know what, that quantity, it depends on what time we're looking at it, but it also depends on where I'm looking. Okay? So for now, at least, right, this is just notation, but x and t, time and space is usually, or space and time, is usually the standard mathy lingo for this, right? Okay, so user, great, okay. Then what is a PDE? I'll write it out all the way. A partial differential equation, which we shall forever call a PDE, so that's a lot easier to say, is just what you would think, or I assume is maybe just what you would think, is an equation relating u, the function here, now Now, if I just said and its derivatives, I could say that, I guess, and be done with it. But I'm going to emphasize here, related to and its partial. Oops. Derivatives. Because, of course, this is where we're going to have to be busting out some of our Calc 3 knowledge, a very limited amount, but right, for a function of two variables, now you probably in Calc 3 did stuff like z equals f of x and y, or something like that, where x and y were the two variables, right, and z was the lettering we used to be the third dimension if we were going to graph this or something. So same idea, right? But for sure, in this case, right, in Calc 3, you did things like the x partial and the y partial. Those were the first derivatives, plural. And then maybe you also did stuff like fxx and fyy, which were second derivatives, partial derivatives. Okay, and hopefully, I think we all remember what those meant. Right, these are the derivatives in whichever direction you indicate. So when I say, of course, here you're doing a PDE is an equation relating units partial derivatives. Of course, by its partial derivatives, I'm talking about these characters, x and ut. These are the first partial derivatives, because you take the derivative once. But we all remember how to do this, right? So to do the x partial derivative, I'm just pretending that t is a constant, or t is a number, and I'm pretending x is the variable in order to get this guy. And then on the other hand, to get ut, it's the opposite. I pretend that t is the variable and u is a constant. Because of course it doesn't make any sense to say the first derivative of a function of more than one variable, unless we happen to have that x is a function of t itself, right? Sometimes we had that situation and we could still sort of muddle through this, but in this case it isn't, right? In this case we're thinking about x and t, time and space, as being independent of each other. So, right, so these, if we talk about first derivative, we mean those two characters, and then of course you might remember, if you do one more derivative, if you go in the x direction one more time, you get uxx. And if you do one more derivative in the t direction for ut, you get utt, which is the second derivative, or the second partials. Sorry, that says partials. Looks a little weird. And then the pieces missing here, of course, are what I think we called the mixed derivatives, maybe, or something like that, which is to go in the x direction and then the t, or the other way, you could go t first and then x. And hopefully, maybe you remember from Calc 3 that for well-behaved functions, anyway, uxt and utx are the same. Okay, we don't need to, this is not super important right now. I'm just kind of reminding you of things you already hopefully know or knew at some point. We are going to use these guys, though. So 1, 2, 3, 4 are going to make some appearances. Okay, these intermediate or mixed derivatives are not going to appear at all. Not in our problems anyway. Okay, but okay. So much like when what we did in the last few weeks of doing systems of ODEs, where basically it's like yeah, same story, but everything is 2D, right? For systems, right? We had a top component and a bottom component. In some sense, this is a similar idea that I'm still going to talk about derivatives, and we're still going to probably use some of our similar tricks, but everything is twice as hard, I guess you could say, right? Or in other words, here I just have two variables. So I have to think about, you could think about x as being the top component and t as being the bottom component. Not quite, not quite, right? But in some sense, we're still kind of thinking, or you could think a little bit about vectors and things like that, but not really. So we're going to have some new tricks here. But okay, so partial derivatives, great, no big deal. Hopefully that's all right. So before we jump in, then, I at least want to sort of say, well, so who are these quantities, these derivatives that we're going to be looking at? So these guys, right? So these four are maybe going to make some appearances. But remind yourself, you already know what a derivative is, right? You've known this for the last 4 years at least, or 3 years at the very least, that a derivative just tells you about how something changes, how the function changes with respect to the variable changing. So ux, for example, this tells you how does u change when x changes. Or technically, when x increases by 1, how much does u change by? And ditto for t. Second derivatives, uxx and utt, of course, those tell those tell you about how the first derivative changes, if you want to go that way, and you could say it just like that. Or of course, you want to sort of tie this together in a fancier format, right? It's the describes the slope, the slope of the slope, you could say, right? Of course, if we were graphing this would be trying to describe the concavity, is the other word that we might have used at some point in our lives to describe the slope of the slope. But let's not get too carried away, right? Uxx and utt should simply tell us how uxx tells us how does ux change with respect to x, and utt tells us how does ut change with respect to t, right? And so we're not going to really use these mixed ones. We're sort of all heading in the same direction for the most part. So there isn't much. I mean, I guess I didn't even write anything down there, right? So I'm just trying to remind you, if you are looking for, oh gosh, what are these things? If u is distance or position or whatever, ux is still something like velocity, but so is ut. Okay, so that's why it's a little funny to say, well, ut is the velocity when you think about t changing. Ux is the velocity when you think about location changing. And we haven't really thought too much about that yet, so we're going to have to do a little bit of unpacking there. And then same thing, right? Uxx and utt tell you about how those guys change with respect to space and with respect to time. The t branch is going to always be much more natural because 99% of the time when we've done word problems in the last 4 years, t has been the only variable. So you know, a derivative, a first derivative, sure, that's speed in your car. A second derivative, that's how much are you hitting the gas. Sure. But those things are going to be a little, while they mean the same thing over here in Spaceland, we haven't really thought too much about what that actually means yet. So we will, though, when we unpack our first example. Okay, so that's it for overview of PDEs. I guess I'm not going to, well, okay, I will say very quickly. Of course, nothing is new here. When we're looking for a solution to a PDE, we're going to look for a function that actually works when you plug it in the PDE, right? There's nothing different about a PDE than compared to an ODE. Same idea. I might have initial conditions that I could use to solve for constants. Everything's the same, right? So there isn't much. I won't say anything or write anything down here. But as we work our way through these, a lot of things will hopefully sound familiar. So the world of PDEs, which is a very difficult world, so part of the reason why we wait until the second half of the semester to do this is just because there isn't a whole lot that we can get our hands on without some pretty sophisticated and fancy math that is above the level of an undergraduate course. So what can we do is that we can at least orient ourselves and do some solving on some of the classic problems or classic models that are used in PDEs to represent a lot of real-life physical systems. In fact, I would actually claim there's really only a handful of PDEs that people actually know about and study. And if they have a system that they want to model, they mostly just try to say, well, which of the famous PDEs is this the closest to? And then they sort of finesse it into that category and use probably a numerical solver instead of doing it by hand. But they would at least use the strategies that we are going to talk about here to solve. So we'll look at two of the three classic and famous PDEs. So the first one is quite simply known as the heat equation. So we'll do the heat equation, and we should hopefully have time to do the wave equation. It's debatable what's 3, 4, and 5. There's a series of others that are really, really hard, but that are really useful. That if you go on to take more in grad school or somewhere else, you will learn about some of these other characters. But heat and wave are not too bad. So what's the heat equation? So I'm going to pose this to you as the classic real life problem that this models, and then we'll do some unpacking here. Okay, so what is the heat equation all about? So this is So it's going to be a PDE, which I'll write down for you probably in about half an hour. This PDE is used to model, classically, heat, and I'll just put in parentheses, or anything that diffuses, which is just a fancy word for spreads, similarly. So it's classically used to model heat diffusion. Across an object in some medium. Okay, so as a general description of this, where we'll spend at least this week and next week, is the heat equation. So what does this talk about? So the heat equation describes the spread, right? Diffusion is the sort of more thermodynamic word, but diffusion just means spread. So this is to model how does heat spread across an object that's in some environment, medium, meaning, just it's sitting somewhere, maybe just in a room, right? Or maybe in water or something like that. So heat diffusion, right, is what this is trying to model. And there's many other things that model, that diffuse similar to heat. So any of those sorts of things, which there are loads of things that behave similarly, can all be solved and modeled with this PDE that we're going to look at. Right, so while this is going to seem like, oh gosh, this seems like a limited problem that's not that exciting or important, maybe. But I promise you, this setup and idea and solution eventually is used to model an awful lot of real life things, primarily in engineering and physics scenarios. Okay, so let me give you a real life, what's our sort of setup for this. So let's imagine some sort of a rod or bar. I'll go with bar, I guess. That's straight and uniform in material. In other words, you have a rod or a bar of, we'll use metal as our standard substance, but you could do this with some other things. We'll look at some other kinds of things, but so that I have some sort of a bar, a metal bar. It's a straight bar. It doesn't have curves or anything for us to worry about, and it's uniform in material. By that I just mean it's the same all the way across. It's not hollow, it's solid, and it's the same, whatever it's made of. It's made of that across the whole thing. All right, so I'll draw you a picture of the, maybe let me get one more sentence here. Okay. We'll say it has length L. Capital L. And so we think of, going back to our function now, we think of x. So remember how we said x is location. So if the bar has length L, if the bar that we're looking at is of length capital L, then we will think of the locations on that bar as running from 0 to L. Right? So of course, here, let me draw it for you. Right? So I have some sort of tube or whatever you want to call this. Not tube, because it's filled in, it's solid. I'll do it that way. But it's of length L. Okay, so of course, what I'm imagining here is that if this is some sort of x-axis, which I'm not even messing around with the t-axis right now, just x, that I'm imagining this living on a graph, you could say, or on a number line at least, from 0 to L. Okay, so the left end of the bar is located at L, at 0, and the right end is located at L. And so, of course, any x value in here, or here, right? These are possible x values, which should describe, so when I said at the beginning of the video, x is location or space, this is what I mean, is that we're going to be studying this bar, and we're going to be applying some heat to it. So x refers to where are you on the bar? Are you at x equals 0? That would mean you're all the way on the left end. Are you at x equals L? That would mean you're all the way on the right end. Or I could be anywhere in between. I could be at x equals 1 or x equals 7 or whatever those other x's I might have drawn in there might be. All right? Okay, so that's our rod that we'll draw a cajillion more times. So then what's our function here? So what are we going to be modeling with the heat equation? Well, is heat. So so our function u is going to equal or represents. So here's an important thing to get straight here. So u is a function. It's a function of x and t. Represents the temperature. Okay, so that's what it's measuring. Of a, you could say, very thin cross-section of the bar at location x and time t. Okay, so since I already have it drawn over here, so this is a metal rod or a metal bar, fine, and maybe the whole thing is heated up to, I don't know, 150 degrees. Okay, in that case, the temperature is 150, whether I'm at x equals 0 or x equals 1 or x equals whatever. Okay, if it's all the same, fine. They could all be the same. So in that case, u would just be equal to whatever the temperature is. But then two things might not be true, right? So that's sort of a dumb, easy example. What though could be true about this is it could say, well, maybe actually you have heat in the middle. In other words, you have a fire here. Sorry, that's my comical fire. Well, then this might be hotter here than, let's say, further away. That's probably true. So maybe the temperature here would be 200, but down here the temperature is only, 100 or less. So that's what I mean when I say, of course, it depends on on the x value. Maybe if I'm right in the middle, it's hot, but if I move away from the middle, it's cooler. That might be. So that's one thing. Oh, another thing might be to say, well, let's say that the bar is exposed to heat that's happening, in other words, or coolness that's happening. Well, then this might change over time. So maybe at some time, maybe the whole bar is 200 degrees. As 100 degrees, but then you start heating up the middle. Well, this might be more later on. So it may also, of course, depend on time. So that's why we say, so U represents the temperature of this bar at location X and time T, both of which may, and in fact probably most of the time will, make a difference. Okay? Now, one comment here, right? You might say, oh, gee, I don't know what you mean by this very thin cross-section. Well, so what do I mean here? Or what's, of course, the idea is that I might take a little slice here and say, oh, okay, if this is, I don't know, I'm just going to make up a number here. Maybe that's x equals 3. Then if I would imagine myself sort of taking a very thin little slice right here at at location 3, and I smack a thermometer on this little piece of metal, and I measure how hot it is. Okay. That's what I mean by a cross-section. So, of course, we will assume, because we're not going to try to totally kill ourselves here, we will assume that the temperature is uniform. In other words, it's the same across the entire cross section. So in other words, we're not going to be too worried about the, oh my gosh, my cross section, what if it's hotter up at the top of my cross section than down at the lower end? Okay, I mean, we're not going to do that. That's just even, that's a little too crazy. Right. So we're going to assume that wherever I slice this, if I was to be able to measure this, which of course in real life I'm not doing, right? But yeah, pretending at least that I could do that and remove a thin little slice, I'm going to assume that that slice is the same temperature. That's actually probably fairly accurate, unless this is a very thick piece of metal. Probably it's roughly uniform throughout the slice. Now again, that's not to say that the temperature here is the same as the temperature here, though. Right? You might have, again, a hot spot over here and cooler over here. That may be. Right? So those aren't going to be the same. But at least across the whole disk, we'll assume that that we have the same temperature. Okay. And so what might this look like? So I'm going to draw you a very large picture because this is all still, but we'll at least agree that this makes sense in terms of our human knowledge of what would happen if we set up an experiment like this. So I'm sorry. So let U of T represent the temperature of various things. We'll assume the temperature across T. And so, of course, our goal is, can we set up, that's a big question, and an even bigger question is solve a PDE that models the heat transfer or heat diffusion across the bar. Oh, I forgot a pronoun there. Can we set up and solve a PDE that models how heat flows, diffusion, right, flows across the bar, subject to, whatever the setup is for the problem? Okay, of course the answer is yes. But before we try to get a model together, let me just do, like I said, let me draw you a big sort of picture here, and we'll hopefully see if this makes sense. All right, so what I'm going to do for you here is, let's imagine, this is just a good thought experiment here. So let's imagine applying a heat source to the center of a cold bar. Okay, so here's where we're going to use, we all have plenty of human instinct here, and I would claim in the kitchen and things like that, you've done heat diffusion experiments before, you just didn't know it, right? Every time you turn the stove on, you're doing a heat diffusion experiment, because of course what happens, you put a cold pot on the stove and you turn the stove on. It's not immediately hot. I mean, you can probably touch it for, I don't know, a minute. Maybe don't try this at home, right? But unless you get really super bored being stuck at home. But it is an instant, right? It doesn't instantly become hot. And same thing on the other end, probably more so that end that we've all gotten into trouble as kids, or not so much kids, of you turn the heat off. Well, we all know that we don't probably go grab the pan right away, because just because the heat's off doesn't mean, of course, that all of the heat has dissipated yet. It takes time, right? But we also know stuff like, oh, you know what I bet gets hot first? The part of the pan that the flame is hitting, and that it takes longer for that heat to reach maybe the sides of the pan or the handle of the pan. Right. So we know heat, we at least have as humans some idea about how heat spreads. So let's imagine that we have this bar, and it's cold to start. By cold, just, nothing unusual about it. And then we apply some heat to the middle. So again, a flame or a candle or something like that. Let's at least point out that what I'm about to draw for you is a reasonable schematic of what might happen. So let's imagine that it's of length 8, first of all, just to have a little nice round number here. So I'm going to draw it. So here's our bar. Maybe I don't want it quite that long. Let's imagine that it has length 8. So I'm just going to label the locations on the bar. as this going from 0 to 8. Obviously that means 4 is in the middle. And I'm just going to put the whole numbers on here, just for reference. Obviously, I could say this about any of the numbers on the number line, not just whole numbers, but this is good enough. So let's imagine that the rod, or the bar, is of length 8, and we're focusing, for the purpose of this example, at the temperature just at the whole numbers on the number line here, 0 through 8. Okay. And when I start, let's imagine that the bar is cold. By that I just mean it's whatever the room temperature is, or since we're going to go for some easy notation here, let's assume that it's 0 degrees, so it's in a freezer, I guess, of some sort, and that it's 0 degrees across the whole bar. So I'm going to say, first of all, at time 0, this is a picture that I'm drawing. We're going to draw two more, so if you're thinking about space, we're going to do time equals 1 and a time equals 2 below this. Right? And what am I imagining that the temperatures are along the bar to get started? Let's say that it's a cold bar, so I'm going to assume that U equals 0. I want to go above. Maybe I'll go, yeah. So let's say when I start at all of these spots, U is 0. 0, 0, 0, 0, 0, 0. There. Okay. Now, right, okay, so that's what U, right, at all locations. So in this case, U is 0 at every location at time 0. Great. But then I apply some heat. 4 is obviously in the middle, right, so I imagine that a flame is sort of ignited. Draw a better flame. It just looks like a webbed foot. Okay, so heat is added to the middle of the bar. Well, we all know, of course, what's going to happen is that the middle of the bar is going to get hot first, but slowly, right, that heat's going to start to diffuse, and the rest of the bar, and eventually, of course, in the long run, the whole bar probably becomes the same temperature. But that takes a while, right? That takes, I don't know, even a pot on a stove, right? Like I said, it takes a few minutes maybe before the whole thing is hot. So if I apply heat at time 0, maybe that's what my picture looks like. But maybe by time 1, my picture more so looks like this. So I'll put my same points on here. These are x values, right? So this is x equals 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? So what might, and U is temperature, right? How might the temperatures look after whatever, second or minute or whatever our time units are? Well, I'm just going to make up some numbers here. But let's pretend that maybe after a minute, these are still cold. But the heat has started to spread out a little bit. This one's up to 5 degrees, 20 degrees. The middle, which of course is where the heat is, where the flame is, maybe that's all the way up to 60. And then probably, unless I have a magical bar, you'd all hopefully agree. I mean, heat isn't like, hey, let's go to the left and not the right, right? I mean, obviously, heat just behaves very logically. So, of course, naturally, whatever the spread is towards the left, it's probably the same as the spread on the right. So if that's how it looks on the left, 0, 0, 5, 20, then probably it's the same on the right. And that might be a profile picture, is what these are usually called, at time equals 1. Of course, I can't write a graph, right? I can't graph for you a function of two variables. Oh, I guess we could in 3D. Okay, good luck, right? I mean, I can't imagine how much of a shit show it was to try to draw any sort of 3D graphs. So we're not going to do that. This isn't too bad, right? I mean, this is still a reasonable graph, but this shows you all the same information. It's showing you how does this change over time, but also how does this change when you look at location. All right, let me just draw one third picture, and then we're going to come up with some smart things to say, hopefully. So a third picture is maybe after one more second, or minute, or whatever. And by then, of course, we all know what happened. The heat would have hopefully, or will have spread even more. And so what might be true at these x values is that I might have a temperature. Maybe on the edge it still hasn't quite reached there, hasn't reached the edge yet. But slowly, right, these temperatures are starting, the heat is starting to move, so maybe that's up to 5, maybe that's up to 20, and maybe that's up to 60. In the middle, which is of course where the flame is, maybe that's really gotten quite hot, 150. And then again, symmetry would probably dictate that you have the same values on the right side too. And that's a profile of what this rod would look like 2 minutes or 2 seconds into the experiment. Okay, so far so good, right? So I'm not hopefully saying anything too weird here. I just made these numbers up. As you can probably see, I didn't 100% just make them out of thin air. I've obviously gone for a little bit of a connector here, but you know, this is all reasonable, I think, right? I don't think I'm saying anything too crazy here. Aha, okay, so what have you not had to do a whole lot of, and we're not going to start doing it now either, is being the person that's just like, hello, real world. If I need a model to represent a physical real-life problem, where does that come from? For example, we looked at predator-prey model when we were doing these systems. I suppose that's not like a genius to come up with that idea. In fact, we sort of talked about it and reasoned our way through that, oh yeah, okay, you know, the birth rate of one, or I'm sorry, the presence of one species has some influence on the other one being able to survive, and okay, we sort of reasoned our way that that was a reasonable model to use. But if I want to come up with a PDE, right, or some model for this heat diffusion that I see on these 3 little profile pictures here, I don't know. I mean, I'm trying to come up with something with, I'm trying to come up with a differential equation here, which means I need to think about, oh, okay, is there a relationship, right? I mean, just to remind you, right, a differential equation should look, if this was ODE's class, I don't know, if I could somehow say, oh, the second derivative is, you know, I mean, I'm just making shit up, right? But is the first derivative plus the function? Yeah, maybe, I guess. But I mean, I have a real thing here that we're looking at. How do I connect these things? What the process that I'm seeing here? So obviously we're not going to completely reinvent the wheel, but I do want to show you, and mostly this is so that you get familiar with what do these things represent, that there's at least something that we might be able to extract from this. And if we were going to make at least a guess, what the PDE actually turns out to be is actually reasonably well supported by these pictures. So I'm going to add a few things to our little profile here. So hopefully you left yourself some space as I did here. So, So in trying to write down a differential equation of any sort, I'm really trying to establish how does this function and or its derivatives relate to each other. That's what any differential equation we've looked at has been like that. Okay, well here's the function. Now I don't actually have a graph of u, but if I wanted to, right, I mean, I'm going to erase this immediately, right, but this is my graph of u in that picture is just a horizontal line because u is 0. My graph of u in this picture is, you know, some sort of parabola, I guess, or it looks like a normal curve. And then it's, okay, then it, yeah, I guess, right. So, I mean, I could draw you three pictures. If you don't like those numbers that I did in red, you could do little graphs like that. But then how do I compare vertically, right? Because I have to sort of tie together time and space. Okay. So how are we going to come up with this? So let's just do a simple thing first. Let me at least just put some characters in our picture here. So one thing I'm going to do is I'm going to just simply get a handle on how much is u changing by with respect to time. So by that I mean, here's time 0 to time 1. Well, I can talk about temperature change when time changed from 0 to 1 simply by comparing from the previous profile picture and saying, well, how did the temperature change? Well, to go from here to here, what happened? It changed by 0. To go from here to here, it changed by 0. The temperature changed by 0. Now to go from here to here, the temperature changed by 5. Okay, and obviously I'll get us out of our misery here. Of course, since it started at 0 everywhere, the amount it changed by is simply, of course, the new value. Okay, and I'm going to do the same thing for 2 versus 1. So I'll do the same thing. So how did it change from here to here? That's once again nothing, no change. But from here to here, it increased by 5. Now from here to here, it increased by, what's that, 15? From 5 to 20. From 20 to 60, it increased by 40. 60 to 150 is 90, I think. And then symmetry, so same numbers over here, 15 and 5 and 0. Now I think it's important for us to note, though, what are these blue numbers that I just wrote in? These numbers are how much did U, which is the temperature, change when I examined time changing from 0 to 1 and from 1 to 2. So these values here are, I don't want to clutter our picture too badly here, so I'll just stick with colors here, right? These are approximations, anyway, for the t derivative of U, both of these. Because what did they measure? They measured how does U change when t changes by 1. That's what we just did, right? So these numbers in blue, right? So I'll circle one, for example, 20. That describes the t derivative of U at x equals 5, and I guess at t equals 1. Now here, of course, we're doing very rough approximations for derivatives here. We're just doing the old-fashioned algebra 1 rise over run formula, so this is not very official. But at least these numbers, right, these blue numbers are estimates for ut. That's the first derivative with respect to t. Now, why did I write these down? A, so that we get familiar with what does ut actually mean in real life. Okay, it's temperature change per time, or as time changes. But, okay, if I'm trying to establish an a differential equation, it's the case that I'm trying to relate a mystery function. Again, I don't know who u is. I don't know a heat equation yet. But I'm at least trying to see maybe its derivatives are related to each other somehow. So I've at least drawn for you in blue here some approximations for ut. Okay. But who's my other derivative here? So let me switch colors to orange. So how else, though, does temperature change? This is the one that's a little weird to think about, right? But bear with me here. Don't think now about time changing anymore. We already grabbed that. That's in blue. But how else might we think about a rate of change is as we read the rod from left to right, how does the temperature change? That's the x partial derivative, which again is a little bit of a strange duck. But I'm going to draw that in for you below each of these graphs. So in this case, this is the easiest, right? If I read from left to right, how does the temperature change? Well, it changes here by 0. And it changes between those two by 0 and those two by 0. Okay, right, so these are all zeros. Okay, well, that's not too exciting. But I at least have a little bit more of an exciting one in the next picture here. So again, I'm measuring temperature change per space, or per x. So when x changes by 1, which of course is me doing these things, right? That's x changing by 1. How does the temperature change? Oh, okay. Well, in this region, or in this, it doesn't change at all. Oh, that's nice. But in this one, it goes up by 5. In this one, it goes up by 15. And from here to here, it goes up by 40. Now on the other side, to go from 60 to 20, of course, that's negative 40, and then negative 15, and then negative 5, and then 0. Okay, let me just fill in this last picture very quickly here. So plus 5, plus 15, plus 40, plus 90, minus 90, minus 40, minus 15, and minus 5. And what are these orange numbers? These orange numbers are U x, u x's, I guess I should say. Okay, so this is just old school, right? I'm not doing anything too fancy here, but the x derivatives we have to think a little bit about because we're so we're predestined to think about, when I think about a derivative, I almost always think about, well, tell me how it changes over time. Which that's one type of derivative, but another type of derivative is tell me how it changes over space. Well, that means, or location. Well, that means read any one of these temperature profiles from left to right and tell me about how the temperature changes. Okay? So of course, right, I mean, we all observed, I didn't write it down, but let me go back to blue for a second here. Of course, in all of my pictures, all of the blue numbers, they're all positive, isn't that right? So in this case, of course, u is positive, or 0, I guess, right? It could be equal to 0. Everywhere, right? Which, of course, that makes sense, right? Again, the t derivatives are easy. Well, of course, the temperature is rising. So, of course, the t derivative should be positive, or 0, because the temperature is never falling. Duh. But going back to ux, though, well, here, ux, I'm going to erase this just because I don't want to ruin my picture here. But in this case, ux is positive, or 0. But on the back half, ux is negative. And ditto for the picture below. Now, all of this is to say, aside from drawing cute pictures and busting out lots of colored pencils and whatnot, what do we think about an idea? So here's where I'm going to ask you something about this later on. Hypothesis. ut is somehow related or, proportional. Here, let me do it that way. It's proportional to ux. Question mark. So, right, I mean, we're at this point, we're just sort of, I don't know, we're just drilling for oil here, just trying to hopefully strike rich at some point. But, well, all right, I mean, this would be a PDE, our very first one. But look at these two little profiles we did here. Notice, of course, UT is always positive. Look at all the blue numbers. They're all positive. Okay, so over here, this is always positive, evidently, or 0. Over here, now UX, well, UX switches from being positive in the first half to being negative in the second half. Ooh. So, I mean, right off the bat, that can't be our PDE. Because, right, this is always positive, and this switches from positive to negative. So whether, I don't even know if k is positive or negative, who cares? You can't possibly have something that's always one sign, and this that switches signs? Never. Oh dear. Okay. And yet, in some sense, what I just wrote down is not a terrible idea, because, of course, what did I just erase? Is something that said, well, the rate at which temperature changes over time is related to or is proportional to the rate at which it changes over space. Well, they're both measuring temperature, and I'm not actually doing two experiments here. I'm just putting a candle under this piece of metal. So in some sense, there should be a connection between these two derivatives. And yet, that doesn't work, right? So ux, no. Ux can't, I'll leave the orange in the picture here, right? But let me just erase that so I have space to finish my picture here. So I don't think that works. I think we strike out on that those two guys are not going to be related to each other directly anyway. So I guess, when people were trying to think about, well, how else could I tie these together? Somebody finally had a good idea and said, well, but there does seem to be a pattern here, or there does seem to be a connection. And the best way to see that connection is to do one more round of my little what's the difference thing, right? These are like little logic puzzles that we did. So let me do one more round of how much does the orange change by from left to right. So to go from 0 to 5, of course, it increases by 5. To go from 5 to 15, it increases by 10. To go from 15 to 40, it increases by 25. Okay. Now, to go from 40 to negative 40, it goes down by 80. So we'll put a pin in that for a second. But let me keep going. To go from negative 40 to negative 15, that's plus 25. Negative is plus 10. And negative 5 to 0 is plus 5. And let me just fill those numbers in quickly down here too. Same thing. Plus 10, plus 25, plus 50, minus 180, plus 50, plus 25, plus 10. Am I to the end? Yeah. Oh. Okay. Did I goof this somewhere? Oh gosh, I think I did. 40, 90, minus 90. Oh no, okay, I'm alright, I'm sorry. Oh, I was looking at the wrong thing. Yes, okay. So hopefully I did second grade math correctly, of just doing subtractions. Okay. So first of all, what did I just put in? This was purple that I just did. What did I just put in purple? Well, orange was UX, right? Orange was describing when I read from left to right, so that means it's the X direction, the rate of change. Well, that's the derivative. But what did I do in purple here is I looked at how UX, those were these orange numbers, I looked at how UX changed from left to right. So purple was actually UXX. Same down here. In other words, the second derivative, right? Well, either I'm just torturing you unnecessarily, which is always a possibility, or I did this for a reason. So now is where we're going to have to be a little bit squinty at the screen here. Oh gosh, I don't mean to be busting out yet another color here, but black. Let's just go straight up black here, since this is going to be the right answer. So let's just do one little comparison now, if you would, for me. So first of all, what do we notice about the UXXs? Is that aside from this number in the middle, right, so we're going to have to put a pin in the number in the middle for a second. All the other numbers are positive, right? Isn't that true? All the other purple numbers are positive. So in fact, sorry, this is black, but it's close enough to purple. So this is positive almost everywhere, except right in the middle. Okay, and now here's where I'm hoping you can squint with me here a little bit. Look at the blue numbers and the purple numbers. Again, except that one in the middle. And then same thing down here. Blue versus purple. Okay, so let me go first example up here. So if I look at the blue versus the purple, I'm trying to see if there's at least a relationship here. So don't worry about the middle number. But what happens to blue? Blue goes 0, 5, 20. Purple goes 5, 10, 25. So increasing. Okay, skip over the middle. And then it goes 25, 0, 0. And 20, 25, 10, 5. So decreasing. Let's go to our second picture at the bottom here. Blue goes 5, 15, 40. Purple goes 10, 25, 50. Again, sort of a similar pattern. Anyway, not exactly, but okay, increasing. Okay, decreasing on the right side. So, what are we, let me clean this up a little bit and erase my black circles here. Is that aside from the middle, now the middle, of course, at 4 is where we have the heat, is at the middle. So there's going to be some very strange behavior right there. So let's forget that or ignore the what's happening right in the middle. But apart from that, everywhere else, it's at least believable that the blue values and the purple values that we ended up with are at least related, and I'll use the word proportional to each other. When one goes up, the other goes up. When the blue goes up, the purple goes up. right? That's pretty much all we're looking for in order to say, oh, all right, yeah, those are proportional. Okay, so the idea is, hopefully, do I have space here? Okay, I'll put a little comment here, right? Is that maybe we can, hopefully we can see, I'll assert, we can see, maybe just put this below this if you want, or off to the side, that at least it looks like UT might be proportional to, or related to at least, UXX. Okay, not UX, right? It would be pretty bonkers to try to say that UT is proportional to UX because of the whole sign thing. But UXX follows along a similar pattern as UT. And this is a groundbreaking, this is not a proof by any means, but this is at least a nice little exploration and an example that suggests that that's true. And this is a huge connection to be able to say, oh, well, if there's a way for me to link UT, T derivatives with X derivatives, then perhaps I'd be able to solve this and wrap all of these, changing factors together into a nice, solvable problem. And indeed, so now I will give you the punchline. Thus the heat equation is born. All right, so here it is. So the heat equation, or I should say the PDE for the heat equation, often denoted HE for heat equation, obviously, as it turns out, is exactly what we just said. UT is proportional to UXX. Now, most of the time when we've said something is, A is proportional to B, we've said something like, oh, there's a constant in front of it. And that's what we're going to say here, too. Now, I'm a big fan of K, since that sort of makes us think of constant, or C. But we'll stick with sort of more standard notation, and you'll see why it's called this in a minute. The constant that's usually in front of this, since math people love Greek letters, it's alpha. That looks like a little fish. But we actually will use alpha squared, and you'll sort of see there's a reason for doing the squared thing later on. But this is the heat equation, so where alpha squared is called the thermal constant, or sometimes thermal diffusion, if you want the full fancy name. Coefficient or constant. Okay, but I feel like putting, I don't know, like exclamation points around this. I mean, it's simple, right? It's not that long, right? And this is the PDE that governs heat transfer or heat diffusion, is that. Alpha squared is a number, right? So don't freak out about that. And in case you were ever so slightly curious, right, alpha squared is, of course, a number, a constant that measures. It's a measure, really, of how quickly measures how quickly heat spreads across the material in your problem. So in case you're just ever so curious about different famous metals or famous substances that you might use, a metal like silver has a diffusion constant of 1.71, which is, as it's going to turn out, means it's actually quite diffusive. In other words, heat travels very quickly across silver. I have some other elements in case you. Iron, it's about 0.12, which is sort of medium-ish. Other things, it doesn't have to just be metal. Brick has a diffusion of, if I copy these down right off the internet anyway, 0.004. And water, which we don't think a whole lot about, has a diffusion constant of 0.001. So not very quick to transfer. These numbers don't matter, so don't worry about any of them. Obviously, in the problems, we'll be given a number to fill in for alpha squared. Okay. It's going to always be positive, though. I guess maybe I should have said it is a constant. And that's why we call it alpha squared, is because, and it's always positive. Right? Because it's just some measurement of how quickly heat spreads across the material. Okay, so we have our PDE. That's okay. So that's the thing we're going to have to try to somehow solve, which we have no idea how to do yet. But well, it's probably going to involve some of our old techniques that we employed in the past, making a guess and plugging it in and all that good stuff. So before we get to that, which I think we'll do in our next video, is the solving piece. Just one last bit about the setup here. So I put a nice box around this because that is the heat equation, very famous. Now, of course, what do we usually have when we have, or when we're talking about a differential equation, is of course we usually have initial conditions, right, or initial points that we use usually at the end in order to solve for the constant or constants in our problem. And the same is going to be true here. But I'm not going to have initial points, because hopefully that wouldn't make any sense, or maybe I shouldn't say it wouldn't make sense, but right, me telling you the initial temperature here, I mean BFD, right? That's not much information telling me that it's 80 degrees at x equals 3. Well, how hot is it here? How hot is it here? Ooh. Okay, so I'm not going to just have a point as my initial condition. I'm actually going to have a whole function, which is going to describe the heat, or the temperature, across the whole rod, or the whole bar. All right? So rather than just having a single point as an initial value, or initial values, we're going to have what's usually known as an initial boundary condition. So I'll say instead of some initial point or points, we'll have, in this case, just one, an initial boundary condition, namely, we will know the temperature profile at time 0 across the whole rod. So namely, we will have some function which we're going to label f of x, so little f is back in our lives, so little f of x, which is just defined as notation to be the temperature at x, at location x, but time 0. Right, so of course, what is this? So this is the initial, since it's time 0, temperature profile. Across the rod or bar, whatever we call it. But it's a function, right? I can't just get away with a single value. I have to describe for you, okay, tell me the temperature everywhere. So I better have a function for that. And we'll use f of x for that, just because we like f. We like f of x. All right, so we will be given, or we need to be given this, right, f of x. And we need it for x between 0 and L. Right, remember, that's the bar. Right, it goes from location 0 to location L. So we have to be given in these problems an f of x, which is going to represent this initial temperature distribution, you might say. Okay? To make our lives easier, and because it's sort of real life too, generally, we assume that there's symmetry. So generally, we assume that the ends of the bar are the same temperature, and since we're sort of creating a system here, we can assume that that temperature is 0, just because numbering system. So generally, we assume that the temperature at the two ends are equal. In other words, we're doing a symmetric kind of an experiment here. And without loss of any generality, and since it'll make our math easier, that it's 0 degrees. Okay, so, right, so maybe for example, I'm just going to go to a new slide here, so let's get out space here. So for example, we might have 25 minus x minus 5 squared for a rod maybe of length 10. Okay. So this might be, let's come down here, an example of an initial boundary condition for one of these. Okay, because of course notice at 0, if you plug 0 in there, I think you get 0. Right? If I run 0 through there, you get 25 minus 5 squared, or negative 5 squared, I guess, which is 0. And at the other end, which is 10, you also get 0. But of course, right? What is this saying about the rod? Is it saying that what is the temperature profile at time 0? Oops, give myself a little more space here. I'll do it over here. And so here's our rod. So what is the temperature profile at time 0? So this is initially at time 0 when you start your experiment. This is a parabola. Right? This is an upside down parabola. So apparently it looks something like this. The temperature okay, in the middle here at 5. What is that, 25? So the temperature's, it's hot, or I don't know if 25 is considered hot or not, depending on what scale you're using, I guess, but right, the temperature is 25 in the middle of the bar, and then of course as I go towards the ends of the bar, it's 0 on both ends, right? So temperature is 0, but it's warmer in the middle with the heat. So maybe this is an example of a problem that got started a little while ago, but for whatever reason, maybe we're just going to start observing it now, and we're going to call this time 0, which is when the middle of the bar is quite hot, and then as you go to the left and the right, it becomes less hot. So maybe this is an example of you've heated this thing up with heat in the middle, and then you turn the heat off, and we actually want to observe the you might call it cold diffusion, right, or the heat diffusing, or I should say escaping, not, and in which case we might, and this model would work for that too, right? So the heat diffusion, whether you're adding heat or removing heat, or letting heat burn off, so to speak, the same model is used, right? So this might be an initial boundary condition that we have. But the point is, right, is that in order to know enough information about the original state of the system, I have to be told the temperature across the whole bar. And the only way for me to do that is to give you a function. Okay, in an easier example, like in the one that we documented here, right? My initial temperature profile was just 0 everywhere. Okay, well that's fine. I mean, that's the easiest thing that we could probably ever have, but it doesn't always have to be just 0, 0, 0, 0, 0, 0. Maybe this, maybe it's this. All right, so of course then, right, the idea is that to phrase our problem, or to sort of pose our question, our heat equation, which we'll solve next time, so the full heat equation, I'll just squeeze it in here. So the full heat equation, HE for heat equation, is, so UT equals our constant, whatever that is, UXX, and, or with, like we usually state the initial conditions off to the side, with some initial, with f of x being the initial temperature, so at time 0, that's what that 0 means, at time 0, and at position x, f of x, whatever that might be, describes the initial temperature, maybe like this example right here. Okay, and we're running this for x between 0 and L. So if I was going to put a box, I would probably more so do this box, because that's got the whole story now. Okay, so it's going to be our goal to say, all right, so either manufactured WebAssign problem or real life, I'm working in a lab problem, says, oh, okay, I looked up, I Googled this constant because I'm making something out of, aluminum. So I looked that up, great. Okay, I can certainly tell you that. That's just present. That's just tell me the temperature right now. You could do that, right? You would know that if you're in a lab and you're about to run some experiment. You could say, yeah, okay, the initial temperature is, 50 degrees across the whole thing, or, or something like this. Oh, all right, you could probably do that. So this isn't super far-fetched. If I'm trying to bring this baby in for a landing here, I would say, while I know there's a lot of stuff swirling about here, and when we go to solve this, it's going to be a little bit messy, this is not a totally unrealistic real-life situation to be in and ponder the question, so how to solve this and get a solution. Because, of course, that's what this is all about, right? It's not actually having to do the experiment where you heat this thing up and possibly have it explode on you or whatever. You want to say, well, can I model this and predict, is this going to blow up on me? Of course, real-life people that build stuff have to do stuff like this all the time, where they have to be concerned about, I'm making this bridge, and when it's 120 degrees outside and the friction from the cars running over this bridge, is this heat going to build up too much that the bridge is going to melt, right? Or the equivalent of melting, right? So, okay, I've said enough about all of this. So, so as usual, stay tuned for more details. And in particular, we need to certainly come up with a pretty good strategy for solving that thing. But it's pretty cute, and I don't think it's not too awful. So, okay, so I'll see you in the next video.